Talk a little bit more about derivatives and the derivatives of some of the functions that we've been leaving out. So specifically the logarithmic function and the inverse trigonometric functions. Now, in order to talk about the derivative of these functions, we actually really have to go back and think how they're even defined. And these functions are examples of what's called inverse functions. So they're just simply defined to be the inverse of a one-to-one function. So what we're going to land in on is how to take the derivative of an inverse function. Okay, so let's go back and think about what an inverse function is. So if I have a function f of x, and f of x is 1 to 1, and now f of x may not be 1 to 1 on its natural domain. We may have to restrict the domain so that it is 1 to 1. So we'll just say that f of x is 1 to 1 on some interval a to b. Then what we know is that f has an inverse. Or in other words, another way to say that, maybe a more technical way to say that, is that the inverse function is well defined. Okay, so this is like the situation when we have an exponential function. So if f of x is an exponential function, it's going to be 1 to 1 for all real numbers. And then the inverse is well defined, and the inverse is the logarithmic function. And so the question that we have is that, let's say we know f prime of x, so we know the derivative of f, okay? And we know what the inverse function is, okay? Or we know that f has an inverse function. So here's the question. The inverse function is just defined to be, the function that kind of undoes the operation of f. And if we know the derivative of f, so we know how f changes, the question is, can we figure out how the inverse function is changing? Or can we find the derivative of the inverse function? And amazingly, the answer is yes. So what is f inverse prime of x? And so notice the notation is a little tricky, but we're just saying, okay, we're taking the inverse function of f and taking the derivative. Okay? So let's see how it's done. So amazingly, how we find the derivative of an inverse function is just a very simple application of implicit differentiation. Okay, so let's see how it goes. So all I know about f, so I have a function f of x. So I know f prime of x, and I know f inverse of x. What's the only thing I can say about f and f inverse? I can't just write down what the derivative of f inverse is. I have to somehow use the fact that I know the derivative of f of x. So we need to go back to the relationship that f and f inverse satisfy. So recall that to be inverse functions, if I compose f with f inverse, what do I get? Well, f inverse is going to take x to something in the domain of f, and then f is going to take that something in the domain and send it back to x. Okay, so f of f inverse of x is just x. But this is an equation relating f and f inverse. So using implicit differentiation, we can actually relate their rates of change, or their derivatives. So what I want to do is implicitly differentiate this function, or this equation. So we're going to apply implicit differentiation. And what do we get? So this is a composition of functions. So I should take the derivative of the outer function, so f prime of, I leave the inside alone, and then I multiply by the derivative of the inside function, which is f inverse prime of x. So that's the derivative of the left-hand side. But then the derivative of the right-hand side is just 1, right? Derivative of x with respect to x. But look, this is what I'm looking for. I'm looking for the derivative of f inverse. So it seems like I should just divide by f prime of f inverse of x. And that's exactly what we do. So f inverse prime, so the derivative of the inverse function, is nothing more than 1 over f prime evaluated at f inverse of x. Okay, so this is sometimes called the inverse function theorem. Well, the inverse function theorem tells us that this basically makes sense under mild conditions about f. So, notice that we don't want the derivative of f to ever be 0, otherwise this is going to be undefined. But yeah, that's basically it. So this is the nice formula we have for the derivative of an inverse function. And it's really cool that to find the derivative of an inverse function, all I need to know is the derivative of the original function and the inverse function itself. Okay, so let's actually apply this inverse function formula that we have. And so our first example is going to be the logarithmic function. So let's let f of x be e to the x. And recall that we know the derivative. The derivative of e to the x is just e to the x. Okay? And then similarly, we know that e to the x is an exponential function. It's 1 to 1 for all real numbers. So we know the inverse. And the inverse is the natural logarithm, natural log of x. So I'm actually, instead of just plugging everything into the formula, I actually want to kind of go back through the details so you really see how this kind of derivation of the derivative of an inverse function looks like. So what do we know? Well, here's what I'm going to do. I'm going to actually let y be natural log of x. Okay? So I'm just saying y is a dependent variable. It depends on the independent variable x. So it's an explicit function of x. And then what I want to know is the rate of change, dy dx. So here's what we do. I can't just take the derivative of this because I don't know what it is. But I do know the derivative of e to something. So I'm going to use the fact that if I exponentiate both sides, so I have e to the y is equal to e to the natural log of x. So all I did, kind of like, multiplying both sides of an equation by 2, I just took e and raised both sides of the equation into the argument of this exponential function. So these are equivalent. And then e to the y, well, that's just e to the y. But the reason I did this is because when I compose e with natural log, so e to the natural log of x, because they're inverse functions, so I'm taking f of f inverse of x, that's just giving me x. And now I can just apply implicit differentiation. Now we did this in general before, but I think it's good to just see kind of how it goes in a very concrete example. So the derivative of e to the y with respect to x is e to the y, but because this is e to the y, and I'm thinking about y as being a function of x, actually I need to multiply, use the chain rule, dy dx. Okay, so that's the derivative of the left-hand side with respect to x. And then the derivative of the right-hand side is just 1. So, look at that. Dy dx should just be 1 over e to the y. And this actually makes sense. There's no restriction here because e to the y is never 0. So this is the derivative. But wait a second. This doesn't make a lot of sense because we have dy over dx is equal to 1 over e to the y. My derivative function should just be a function of x. But what is e to the y? E to the y is actually equal to x. So using this relationship, I can just substitute in x for e to the y. So in reality, the derivative of the natural log is 1 over x. So this is a very nice, clean formula for the derivative of the natural logarithm. And again, just appreciate the fact that the only way we knew how to find this was by knowing the derivative of e to the x and the fact that e to the x and the natural logarithm were inverse functions. So specifically, we've just talked about the exponential function to base e and the natural logarithm. Now, of course, there are other exponential functions like 3 to the x, 10 to the x, and then of course there are logarithms with other bases. So first, I just want to talk a little bit about the derivatives of exponential functions and logarithms to base other than e. And the nice thing is there's really nothing new if you can remember your change of bases formula for exponential and logarithms. So we're going to pick a number, a, and a is going to be positive, and a is not going to be 1. Okay, and so let's let f of x be a to the x. And I want to take the derivative. Now I don't know how to take the derivative of a to the x in general right now, but I do know how to take the derivative of e to the x. So here's what we want to do. We want to rewrite a to the x as something involving e to the x. And how can we do that? Well, we're going to use the properties of exponents. So if I do the following kind of seemingly arbitrary thing, I'm going to write this as e to the natural log of a to the x. And notice I haven't changed the function, right? Because e composed with log of something is just that something, because they're inverse functions. But now, look, this is natural log of a to the x up in the argument. So what I can do is now use the property of logarithms, and I can actually pull this x out in front. So f of x is really e to the x times natural log of a. But this is much better because this is basically e to the x, but instead of x, I just have a constant multiple of x. So I can just apply the chain rule. So f prime of x is just going to be, well, derivative of e to something is e to that something. And then the price is I have to multiply by the derivative of what was in the argument. So the derivative of x times natural log of a, remember that natural log of a is just a constant. It could just be 1 or 2 or 0.5 or whatever. This is just a linear function, so its derivative is just natural log of a. So the derivative of a to the x, an exponential function, see that this actually is just the same thing as a to the x. So I can really write this as a to the x, if I just sort of reverse this process, times natural log of a. So the derivative of a to the x is a to the x, just like e to the x, but we have to multiply by the natural log of the new base, in this case, a. And you see it's a special case when we have e to the x. The derivative of e to the x will be e to the x times natural log of e, but natural log of e is 1. So everything sort of fits together nicely with this formula. So the next thing we want to do is look at a logarithm of base other than e. So not the natural logarithm. We still are fixing this number a that's positive and not equal to 1. So log base a of x. Again, we're going to do something similar. So we're going to write this in terms of the natural logarithm. But remember that we can actually change the base of the logarithm for free if we just divide by just a certain factor involving the log of the base. So if I want to change to the natural logarithm, the way I think about it, if I want to change base, it's just log of the new base of what you're taking the logarithm of divided by log of the new base of the old base. So this ends up being natural log of x over natural log of a. Okay? If I want natural log, it's just natural log of this divided by natural log of that. But we know what the derivative of natural log is. And again, this natural log of a is just a factor. So in this case, it's like 1 over natural log of a. So now you're seeing why a can't be 1, because otherwise this would be 0, times natural log of x. So it's just a constant times natural log of x. But then we can just apply the constant multiple rule. So this is just 1 over natural log of a times the derivative of natural log of x, which is 1 over x. So if I take the derivative of a logarithmic function to base other than e, I still get basically 1 over x, but I also have this factor of 1 over natural log of the base. So that's kind of the generalization of the derivatives of exponential functions and logarithmic functions. So there's one more thing I want to talk about, and it has to do with a very special application of knowing the derivative of the natural log. And it's called logarithmic differentiation. And I actually have a special name for this. I don't know if anybody else calls it this. But I think about logarithmic differentiation as another differentiation rule. So recall that we had the sum rule, the product rule, the quotient rule, the chain rule. Well, another way you can think about logarithmic differentiation is that it's the exponent rule. Okay, and so why do I call it the exponent rule? Well, because there's actually another way to combine functions that we have not mentioned at all. And you don't really mention it much even in algebra or pre-calculus. And this is the case. What if I have a function, h of x, that's f of x, so some function, raised to another function? So you see h of x isn't like the product of f and g, it's not a quotient of f and g, it's not a composition of f and g, it's really like f of x raised to the g of x. Now there are certainly some assumptions we need to make so that this makes sense, and probably we just want f and g to both be positive, okay, so that they don't take on negative values. That would be sufficient, okay. So what can we do? So you see, this is just really outside the scope of anything we've done before. But the idea behind logarithmic differentiation is that it gives us a way to actually attack the functions that look like this, f of x raised to the g of x. And so the idea is we're going to use the property of logarithms. So anytime you have something up in the argument of an exponential, so anytime you're raising something to a function, the only way we can really get that function out of the sky, so to speak, get it out of the exponent, is to just take a natural log. Okay, so what you do with logarithmic differentiation is you just take the natural log of h of x. And so what does that do to the right-hand side? Well, I take the log of this, f of x to the g of x, I can actually bring the g of x down front. So it's actually g of x times log of f of x. So I haven't done any calculus yet. This is just purely algebra. So you see why we really need f of x to be positive here, because we're taking the natural log of a function, so we better make sure that f of x is not negative. And now what we do next is just implicitly differentiate this relation. Okay, so there's kind of a cool way to think about the derivative of log of something. And what it is, the log of a function is just 1 over the function times the derivative of the function. Okay, that's just the chain rule. So derivative of log of something, maybe I'll even just make a note of that up here. So if I take the derivative of log of something, it's just 1 over whatever I was taking the log of times the derivative of what I was taking the log of. So I just, in my mind, think derivative of log of something is 1 over something times derivative of something. So that's useful, kind of mnemonic to just attack logarithms. So they're really nice. Alrighty. So now if I want to differentiate the right-hand side with respect to x, I got to see that this is a product of functions. But that's okay, because remember, the whole purpose of taking the logarithm was to change this exponentiation of functions into a product of functions. And I can apply the product rule. So this should be g prime of x times log of f of x plus g of x times 1 over f of x times f prime of x. Okay, so again, here I just left g of x alone. I took the derivative of log of f of x. Derivative of log of f of x is 1 over f of x times derivative of f of x. And now I'm almost done. Because remember that I'm looking for h prime of x, so if I just multiply both sides by h of x, I'm done. But I don't want to just leave it as h of x. I actually want to multiply both sides by what h of x is equal to, f of x raised to the g of x. So our final answer for the derivative, h prime of x, is, well, it's g prime of x times log of f of x plus, so all of this I can sort of write as a single fraction, g of x times f prime of x all over f of x, and then times f of x raised to the g of x. Got a little squeeze there, but you see the idea. So we have this factor that we got from logarithmic differentiation, but then we also need to multiply by the original function, f of x raised to the g of x. And I think, if I imagine what you're thinking right now, this is a lot, but in specific applications, you just want to do this process. And in the examples, you'll see how it goes. And it's really pretty simple and straightforward once you get the hang of it. Okay, so we want to take the derivative of these two functions. F of x is an exponential function with base 2. G of x is a logarithmic function of base 2. And if you paid attention to the lecture, we actually have explicit formulas for these. And it's fine if you just want to memorize those. But in this example, I actually want to kind of break it down. So hopefully with a concrete example, this is like the case a equals 2, it helps you see where things are coming from. So before I take the derivative of f of x, I just want to rewrite it. So 2 to the x is the same thing as e to the x times natural log of 2. Okay? And why is that? Well, just remember that this guy up in the exponent is the same thing as log of 2 to the x, using the properties of logarithms. And so then if I just think e to the log of 2 to the x, the e and the log cancel each other out with the composition, and we're just left with 2 to the x. So this really is the same thing. And then I can just take the derivative. And the derivative of e to something is e to that same something times the derivative of what's an argument of that something. So that's just natural log of 2. But e to the x times natural log of 2, exactly as I explained up here, is just 2 to the x. So the derivative is just 2 to the x times natural log of 2. And natural log of 2 is just a number that's a little bit less than 1. So that's it. Here's the derivative. We're going to do something very similar with g of x. We know what the derivative of natural log is. So let's just rewrite g of x in terms of the natural log. So g of x should be natural log of x divided by natural log of 2. That's just the change of base formula for logarithms. You take the log of the argument divided by the log of the base. So then the derivative, we can then just apply the chain rule. Not the chain rule, the constant multiple rule. And knowing the derivative of the natural log of x. So this should just be 1 over x times 1 over natural log of 2. So 1 over x times natural log of 2. There it is. So there's really nothing special. And actually, when I teach, I like to kind of ignore logarithms and exponentials to other bases because they're really kind of unnecessarily complicated. If you ever have one, you just immediately want to change to base e because you know how everything works out in that case. And then you just carry around this extra constant. So there's really not a lot of deep content to exponential functions and logarithms to other bases because you can always just express them as exponentials base e and logarithms base e. Okay, so this is exactly a setup for our exponent rule, or logarithmic differentiation. We have y that is x raised to the x. Okay, so this is like our f of x raised to the g of x. And now, of course, we need to require that x be bigger than 0 for this really to make a lot of sense. Okay, so what do we do? Well, let's just break down exactly like we did in the general case, this specific case. So I don't know what the derivative of x to the x is, but I know that if I take the logarithm, it's going to simplify this into a product of functions. So I can say that natural log of y is equal to natural log of x to the x, and then just apply my properties of logarithms to bring down what's in the argument. So I can bring this x down and change it to x times natural log of x. So I haven't done any calculus. This is all algebra. I'm just manipulating the function to get it into a form that I can actually differentiate. Now, of course, it's no longer an explicit function. It's an implicit relationship between x and y. So I just need to use implicit differentiation. So the derivative of natural log of y is 1 over y times y prime, the derivative of y. And then on the right-hand side, this is just a product rule. So derivative of x is 1 times natural log of x. And then we have x times the derivative of log x, natural log of x, which is 1 over x. But x times 1 over x is 1. Remember that x is greater than 0, so specifically it's not equal to 0. So we have 1 over y times y prime equals log x plus 1. But I want to isolate y prime, so I want to multiply the left side and the right side of the equation by y. So I have y prime is equal to log of x plus 1 times y, but I don't really like the y being on this side of the equation because I want y prime to be an explicit function of x. But fortunately, I know exactly what y is in terms of x. It's just x raised to the x. So then the derivative as a function of x is natural log of x plus 1 times x raised to the x. And that's how it goes. So pretty simple. Logarithmic differentiation has a very nice methodology, kind of an algorithmic way to do it. So it's really nice once you get the hang of it. So here's a function that we could just use the chain rule to differentiate, but I just want to show you how logarithmic differentiation can really simplify things. And if you really like it, it applies in a lot of different situations. And so it's one of those tools, I'm trying to convince you that, there are some situations where you don't need logarithmic differentiation, There are some situations where you do need logarithmic differentiation, but actually logarithmic differentiation is always very helpful, even in situations where maybe you don't exactly need it, but it can be really helpful. And this is a situation like that. Look at what happens when we take the log, both sides of this equation. We have log y is equal to, well, log of e to the sine x squared. The log and the e cancel, so we're just left with sine x squared. Okay? So that actually killed the composition of e and sine of x squared. So now if we differentiate, we get 1 over y times y prime. Notice that when we have y equals something, when we do logarithmic differentiation, we always get exactly the same thing on the left-hand side, 1 over y times y prime. And then the right-hand side, well, this is going to be cosine, that's the derivative of the outside function. And then by the chain rule, we just multiply by the derivative of the inside, which is 2x. So then y prime is, I'm just going to move the 2x out front. It's this function times y, but y is e to the sine of x squared. So there's the derivative. Now, of course, we could have done this by two applications of the chain rule, but we can also do logarithmic differentiation. And you can imagine that if the function was even more complicated, being able to apply those properties of logarithms is extremely helpful. And I think we're going to see that again in the next example as well. All right, so at first glance, this doesn't look like a problem that belongs in this topic, right? So this is really just a rational function. I mean, we have a square root here as well. But before we got to this topic, if I gave you this question, what would you have to do? Well, I see a product of two functions. I see a composition of functions, so square root of a function. And then I have a quotient of two functions. So to do this problem, you would have to use the product rule, the quotient rule, and the chain rule, all in one. And it would be a little difficult. I would not want to do that personally. So this is another case where actually taking the logarithm first of a function greatly simplifies taking the derivative. Because up till now, we've just been using the following property of the logarithm, that the natural log of a to the b is b times natural log of a. But there's also other properties of logarithms we can take advantage of. So if we have the natural log of a times b, we can write this as the natural log of a plus the natural log of b. Similarly, if we have natural log of a over b, this is the same thing as natural log of a minus natural log of b. So not only are we simplifying exponents, in cases where you would have to use the product rule or the quotient rule, by taking the logarithm, we can change that product and that quotient to instead a sum and a difference. So look at what happens when I take the logarithm of this function. Before I do any calculus, let me just do a little bit of algebra. What is natural log of y? Well, here's what it is. It's 2 natural log of x minus 1 plus 1/2 natural log of x plus 1 minus natural log of x plus 2. Now, how did I do that? Okay, well, notice that x minus 1 squared and square root of x plus 1 were multiplied. So when I took the log, I added them. Now really this should have been natural log of x minus 1 squared and natural log of square root of x plus 1, but I also applied the exponent property of logarithm. So the x minus 1 squared inside the logarithm became 2 times natural log of x minus 1. Same thing here. Log of square root of x plus 1 became a half log of x plus 1. And then the quotient, dividing by x plus 2 when I took the logarithm, became minus log of x plus 2. So why did I do that? Well, look what happens when I differentiate. Just like we said before, we always will get 1 over y times y prime. And this is 2 times derivative of log x minus 1 is 1 over x minus 1. And so apply the chain rule. The derivative of x minus 1 is just 1. Plus 1/2 times 1 over x plus 1 minus 1 over x plus 2. Look at how easy these factors of log x minus 1, log of x plus 1, log of x plus 2 were to take the derivative after I spread them all out. And now I'm almost done. So y prime is what I want to isolate. So let me just multiply both sides by the original function y. So this is 2 over x minus 1 plus 1 over 2 times x plus 1 minus 1 over x plus 2. And then all of that times y, which is x minus 1 squared, square root of x plus 1 over x plus 2. And now you really see the advantage of using the logarithm. Because look how much easier this was than using the chain rule, using the product rule, and using the quotient rule to kind of manipulate this out. And somehow this is a nicer form too, because you see it's just, these simple rational factors or terms here times the original function. So it has a very nice form, whereas if we had used the quotient rule, product rule, chain rule, I think it would have looked like more of a mess. It wouldn't have looked as clean and as nice as this case here. So that's how it goes. Another application of logarithmic differentiation, and there you have it.